Now we'll cover section 2, which is our bias studies. So bias studies will be commonly executed using a pattern, usually a gauge block, of very precise dimensions. They will also use the same operator or inspector to avoid introducing unnecessary noise to our measurement. A minimum of 10 measurements of the control pattern or sample will be recommended. You can do 5 measurements or 15 measurements, but a minimum of 10 is a good best practice. Once all the data is collected, we can execute our test as a one-sample t-test hypothesis test. To execute a one-sample t-test with Minitab, we simply use stat, basic statistics, and one-sample t-test. So for example, here on Minitab, I will find the command for one-sample t-test right here. Stat, basic, and one-sample t-test. We will cover this in a couple of moments. Bias studies are commonly executed using a known pattern, usually a gauge block of very precise dimensions. They also use the same operator to avoid variations caused by changing different operators. A minimum of 10 measurements of the control pattern sample are recommended. You can also do the study with 5 measurements of the gauge block or 15 measurements of the gauge block, but a best practice of 10 is recommended. Once all the data is collected, a one-sample t-test hypothesis test is executed. To execute a one-sample t-test, use stat, basic statistics, and one-sample t-test. We will cover this option in Minitab in just a moment. The results of our bias study are simply a hypothesis test where we're asking ourselves, is there any bias on the results based on the pattern data? So for example, let's say I'm asking Andres Ruelas to use machine CMM001. And I ask him, is machine CMM001 biased? To test this, I'm going to grab a 1.5 inch gauge block. I know that in real world conditions, this gauge block is exactly 1.5 inches. I'm going to place it on the machine and I'm going to ask Andres to measure it 5 times. The results are shown here. Now I can grab this data and I can paste it over into Minitab. For people who have never used Minitab before, it's simply an Excel sheet. So if you look at here, you're going to notice that it looks kind of like an Excel sheet. I can record data here. I have an output section here, and I have a simple bar here on the top that allows me to execute different types of analysis. Now, when I copy and paste my information, the first row is always blank. It has no number. This row is known as the title row. I can type in any title name here. For example, I can say title Andres. It has no impact on the data below it. It is simply for recording purposes. Minitab will automatically identify the type of data that is recorded in rows 1 to infinity. In this case, it detects that I have text here. So C1-T, that means that it's a text field. It identifies the equipment used field also has text. So C2-T. And lastly, we have gauge measurement results. It identifies properly that I have only numbers, so that is called C3. If I try and type in a text into a field that is number based, there will be an error message. Now, I'm going to execute my hypothesis test, which is the first type of test that we're going to execute as part of this course. So we're going to do stat, basic statistics, and one sample t-test. After selecting the one sample t-test, Minitab is going to ask me, where is your data? I'm going to say C3, and we're going to do a hypothesis test. The hypothesis is that the data mean should be around 1.5. The data should be around 1.5 because my gauge block is exactly 1.5. So if I'm asking somebody to measure the gauge block over and over and over again, I expect results to be around 1.5. So when I execute my study right here, I will get my output. This output right here is telling me the mean of all my data, the standard deviation of my data, and the confidence interval for my data. In statistics, we always say that the data mean will be the average of my data. So when I asked my inspector to measure 5 times, he might have told me that the part was 1.449, for example. He might say that the part measured 1.495. He might say that the part measured 1.48. He might say that the part was big, 1.52. And at the end of the day, when I add up all measurements together, I will get an average. In this scenario, the average is 1.491. Okay. Now you might notice that this average of 1.491 is not 1.5. So clearly there is a difference. Now, is the difference considered to be significant? Because even though I measure a sample 1, 2, 3, 4, 5 times, I will always get different results. Sometimes I might get 1.51, sometimes 1.50, 1.49, 1.52. So there needs to be a confidence interval of where the average mean will usually fall. In this case, the confidence interval is identified in Minitab as 95% CI, and it goes from a range from 1.485 to 1.496. The value 1.5 is not inside this range, and because of that, the hypothesis test will fail. That means that there is a significant difference. I can conclude that as well looking at my p-value. If the p-value is below 0.05, that means that there is bias. Okay, and if the p-value is above 0.05, then no bias. In this scenario, it was actually below 0.05, so there was bias. Okay, now this might seem unfamiliar to people new to statistics. Please don't worry. Our courses are structured in such a way that we will be doing exercise after exercise after exercise. It is very hard for a new student to grasp the concepts with just one example. So please don't worry, okay? For now, the main thing that I want you guys to look at is that we're doing what is known as a one sample t-test using the same inspector. He's using the same machine, and he's measuring the same gauge block, which in this case is a 1.5 inch gauge block. He is measuring it for the width and determining the output. Now here, I would output and say that there is bias on my measurement result. Additionally, please note that the bias shown here is negative. Why is it negative? Because I'm underreporting the part as being smaller than it actually is. Now let's assume that I did the same exercise with a 1.5 inch gauge block, but I'm now using machine CMM002. Just by looking at the data, I can see that I'm reporting parts as being bigger than 1.5. However, I need to prove it or demonstrate it mathematically. So I'm going to copy and paste my information here. Now, as you might notice, I have worksheet 1 and worksheet 2. You can always add additional worksheets by clicking here on your menu, or within Minitab, typing in the command Control plus N for new. If you do Control plus N, you will get a new worksheet such as this one. Now we're going to do the same thing we did before. We're simply going to select our option for stat, basic statistics, and one sample t-test. We're going to select our column that contains our measurement results, which in this case is C3. We're going to make sure we check the option for perform a hypothesis test, and we're going to type in our hypothesized mean of 1.5. I'm going to click on the OK option, and we're going to review our output. The mean of all my data, which is simply adding up all my data together, is 1.50. Okay, now it will have a confidence interval range. This range goes from 1.53 to 1.513. The value of 1.5 does not fit in this range. It is below the range. As such, the hypothesis test will fail, and that means that there is a bias. When I look at my mean and notice that it is higher, 1.58, is bigger than 1.50, then that means that I have a positive bias. In plain terms, CMM 002 reports parts as being bigger than they actually are. Okay, and I can also confirm it with my p-value. If it is less than 0.05, that means that there is some type of bias. If the p-value is above 0.05, then there is no bias. Okay. In this scenario, since 0.010 is less than 0.05, then there is bias.